All right, so you're going to work on your derivation packet starting today. And so I'm going to do another example of how you do the derivations. So we're going to use Gauss's law to determine the electric field as a function of R from an infinite thin sheet of charge with positive surface charge density. So we're going to go through the steps. And like I said, these are the same steps in your derivation packet. So the first thing you do is you draw the described charge distribution and sketch some field lines. So I've included some different views so we can kind of picture better what's going on. So the sheet is thin, so we don't have to worry about any thickness. So basically, if we look from a side view here, you could picture that our positive charge was made up of essentially just a line of single thickness, like protons or something like that. And that you would have charges essentially on both the top and bottom of the sheet because there'd be no thickness to this at all. So if I were to draw some representative field lines, I would see the electric field lines coming out of the sheet from the bottom and the top. From the simple side view, that's what I'd be seeing, but it's actually taking place over multiple dimensions. So the next thing we want to do is we want to draw a Gaussian surface with symmetry that matches the charge distribution. So there's a couple of different surfaces that you could choose. But in this case, we want to make sure that we choose something that encloses the charge with symmetry. And then we also want to enclose actually only part of the sheet. As I hinted at in the previous video, that if I were to draw an infinite sheet, I'd have to have an infinitely large surface in order to incorporate that. And then my surface area would be infinitely large and I wouldn't be able to do anything. So I need to actually then draw a Gaussian surface that encloses just part of the charge. And then I'll be able to infer what's going on inside of my small portion of my surface. I'll be able to make inferences for what goes on for the rest of it with integration. So what I'm going to choose is I'm going to choose a cylinder. So this cylinder is going through the sheet. It's set up so that the long side here is parallel to the electric field, so that this top surface right here would have a dA vector that's like pointing out, and then the dA vector for like the side would be off to the right. So we've chosen something that has good symmetry with the top and bottom, but is actually perpendicular on the side. This can also be worked with like a rectangular prism. So I've seen this sometimes done with a rectangular prism. I don't like using the rectangular prism because it has more sides. I think it's easier to do the cylinder with only 3 sides, but you could do it that way as well. So we have our Gaussian surface passing through the top and the bottom. So it's capturing both the top of the sheet and the bottom of the sheet. Be careful how you say that. And I'm assuming that my cylinder is finite, so that the top of the cylinder is a radius of R from the sheet, and the bottom of the cylinder is a radius of R from the sheet. I'm going to make sure that my Gaussian surface is on the inside because I don't want to worry about any edge effects. So you saw edge effects in your parallel plate map. So ideally, the electric field for a parallel plate should be just lines going from the positive side to the negative side that are all parallel to each other, so you have a constant electric field. But in reality, towards the edges, those field lines start to bend. So if I wanted to figure out what's going on in the center, I would want to include only just the center. I wouldn't want to choose the edge because what's going on at the edge would not be representative of everything else when we ignore the edge effects. Now, if I didn't want to ignore edge effects, then I would run into problems trying to solve this problem because then I'd have to consider the fact that I can't have these curved lines out here and straight lines in the middle. Technically, everything's curved. It would be a hot mess. So we like to ignore edge effects, that we can assume that our surfaces are very nice and symmetrical with our field. So we want to sketch some representative dA vectors along key surface points. So we have 3 surfaces, so we want to make sure I have at least 3 sections. So I could have a top and bottom. So I'd have a little dA vector for the top and a little dA vector for the bottom, and then a dA vector for the side. So you can see the dA for the top and bottom are parallel to the field and then pointing in the same direction, and that my dA vector here is pointing perpendicular to the field. So that's what I want. So there's going to be no flux through the sides because the E is going to be perpendicular to dA. So if even I had chosen a point over here, that would be perpendicular. Even if I had chosen a point here, that would be coming straight out the page at me. The electric field would still be perpendicular. So the sides have no flux. You're going to write Gauss's law in full integral term and simplify. So we'd have E dot dA is equal to Q enclosed over E naught. And then basically we're going to define what I call A prime is going to be the area of the top or bottom of the cylinder. So that I have an E times A for the top because they're parallel, but I'm going to use A prime. The reason I don't use A is A might be the surface area of like the whole sheet. So that's why I'm using A prime, using a slightly different variable to represent that I'm just using A for that one small purpose of that. And because both the E and dA are both parallel and they'll both be positive fluxes, I can add them. So I get 2EA the top and bottom. And then the sides were 0 to begin with. So now we want to find the surface area. So our enclosed charge is just the portion of the sheet that is enclosed by the cylinder. So that enclosed charge is also going to have an area of A prime. So that the flux that's enclosed is based on that A prime as well. So in this case, our enclosed charge has the same surface area as our cylinder. So that's nice. That doesn't always have to be true. We'll see some examples of that. And then the sheet is in an infinite plane, but the enclosed charge, we're assuming, has the same density. So the portion of our enclosed charge is the same, is going to have the same ratio of charge to surface area. So we're going to use sigma to represent that surface charge density. It's defined it as a positive value. So actually, I don't know my total charge Q for this at all. You could find it, and you'll probably do that in your packet. But in this case, we don't know what it is. So we can, though, use our total charge of the surface area. So, but we're going to do this just for the enclosed charge. So that's going to be Q enclosed for our total charge enclosed by the surface. And then by the surface area of the enclosed charge, that's going to be A prime. So what's really important is that these are for the actual enclosed charge. This is not for the actual cylinder itself. That's for the enclosed charge kind of contained inside of that. So you can imagine that if this was like a thick slab, that I could have more enclosed charge, because if this was like an insulator, I could have charge all throughout there. So I could actually have a cylinder's worth of enclosed charge, not just a circle's worth. So you have to be careful with your definitions of things there. So in this case, our Q enclosed is equal to sigma times A prime. So then we take that and substitute in. So we had previously our Gauss's law was 2A prime equals Q enclosed over E naught. Subbing in for Q enclosed, we get that 2A EA prime is equal to sigma A prime over E naught. The A primes cancel, which is good because we don't actually know what that area is. It was an undefined variable. We defined it. It cancels out. So you'll often do that. You'll introduce variables that will end up canceling out. So substitute everything into Gauss's law, and you end up with E equals to sigma over 2E naught. So we said that for a conductor, for a particular surface of that conductor, that the electric field is going to be sigma over E naught. But because this has both a top and a bottom, our electric field is, that electric field actually has to be divided between the two surfaces. So that's why it's, that's why the 2 is essentially down there, is because the overall field strength is divided between the top and the bottom. So we'll use something like this for to actually find out parallel plates and do a whole bunch of other types of things. So you're going to see lines of charge, you're going to see spheres, you're going to see all sorts of different charge distributions in your derivation packet. But the process is going to be very similar for each. But you have to kind of understand what's going on and why. So if this doesn't make sense to you, please contact me for tutorials. And I can walk you through this again, walk you through different examples, but this is one of the most fundamental things we are going to do all semester. So you really need to have a firm foundation on the concepts about not just the steps you're doing, but why those steps are necessary and how they work.